I would like to present about the topic finite element analysis on tibia with osteogenesis imperfecta. So this is the content of my presentation. OI. OI is known as brittle bone disease. It is caused by the increased bone fragility and decreased bone density due to the mutation of genes that affects the bone formations. The main issue of OI is the prediction of the bone fracture. It is important to investigate the resistance of bone to resist force before fracture. So, what are we trying to solve? From my reading, I have found that currently there is no established clinical method in for OI patients. Limitations where the bone segmented has boundary or presence of gaps, and there is no study of the investigation of all different model, which is whole tibia bone, shaft, and extension shaft. So to address the problem, I have come out with these three objectives. First, to segment the cortical and cancellous. We intend to separate it. Next, to detect the trajectories of the tibia based on the ADL, which are standing on different parts of model. Lastly, to analyze the effect of geometric differences on the tibia models to the theories. To limit the scope of my works, I just only use the right leg tibia. We assume that the both legs will be having the same results because of the same piece of the bone. The DICOM images are obtained from the Hospital University of Malaysia, HUSM. The MATLAB software will be used for the implementations and image validations. The ground truth images are generated by pen.net software. Lastly, the Reconstruction software is used to models and perform the fracture risk analysis by using FEA. So now we come to methodology. The figure shows an example of the DICOM image of tibia proximal region that obtained from HUSM. There are a total of 385 slides of images. All segmentations is performed using pen.net software to create the growth images and iterations of the performed using MATLAB. Here illustrate the blue and red region are selected for the considered ground truth images, which are also called as manual segmentation images, while automated segmentation images are obtained from the previous study by using MATLAB as well. So these are the steps for the image validation. In validations, there are two main categories: standard measures and similarity measures. Standard measures such as accuracy, specificity will be calculated by using the confusion metric. The higher sensitivity and specificity indicate the image algorithm's high quality or performance. DSI is a measurement that used to quantify the difference and similarities between the ground truth and sections. This slide shows how we perform the fracture risk analysis. The tibia models is assumed to be isotropic and the properties. The first figure shows the tibia bone developed from the same module of cortical and cancellous bones. The orange region is the model, while the yellow region shows the cancellous model. Then another figures illustrate the bicortical cancellous model were used for further analysis. In order to study the behaviors of bone in daily activities and their respective 3D tibia models is required for the FEA. FEA is the most common method used to study the bone fracture risk. It discretizes the stress of a small elements that are used to assess the stress of soft tissues. And the patient was a 13-year-old girl, and her weight information promoted based on iron charge, which is 7.5 kilograms, equivalent to 367.9 Newton. Therefore, the same weight was used in these simulations to observe the behavior of bone. In this study, these daily activities include standing and jumping. The loading condition for these daily activities is illustrated in figure. Force is exerted to the tibia bone. The force was applied to the proximal region of the tibia, and the distal end of the tibia stem served as a fixed support to prevent the motion. Based on the nano-indentations tests done by other researchers, the fracture strength was set to 115 megapascal in this study. When the fracture risk value is equal to or less than 1, the tibia is considered fractured. Right, so come to ends. Both of the figures show images from the automated simulations and manual simulations results. From the aspect of the visualizations, the performance of previous result, which is the automated simulation result, is studied. From the technical aspect, the study selected two categories in image validations, which are standard measurement and similarity measurements. The table shows the result mostly are higher than 50%. Term can be considered as ideal. The control color highlights the location of high fracture risk, which experience high bone missile stress level and appear as an orange or red area, while blue color indicates no fracture risk. This figure shows the model are categorized into whole tibia bone, extension shaft, and shaft only. The whole tibia bone is made up of all 385 images, while 285 and 305 slices of stitch were used to generate the shaft and extension shaft respectively. Figure A, B, and C shows the bone missile stress due to standing positions for whole tibia shaft and extension shaft model. Standing, the result shows that all area of the tibia is with dark blue or light blue color, which represents that the bone missile stress is ranging from 0 Pascal to 23 megapascal. Figure A, B, and C shows that most of the area of the tibia is in red color during jumping for whole tibia bone, extension shaft, and shaft model. The jumping, which exerted 20 times the body to the proximal tibia, constitutes the largest area of the vertical region, which is the place that fractures prone to happen. The higher the loading force, the area with higher stresses, color getting larger. From the graph illustrated, we can know that standing has a lower bone missile stress, which is 7.2, 26.79, and 49.84 megapascal whole 3D bone, shaft, and extension shaft model respectively. And for the jumping, it forces the highest bone missile stretch, which is 1,664 and 34, 1,205.65, and 2,243.31 megapascal for the whole 3D bone, shaft, and extension shaft respectively. The bone missile stress of jumping were the fracture strength of 150 megapascal. Apart from that, the bar chart shows that standing has the lower risk of fracture, which is 3.09 for whole tibia bone, 4.29 for shaft model, and 2.1 for extension shaft model. In jumping configuration, the risk values are in the range of 0.05 to 0 in all parts of the models, which means that jumping will definitely cause the tibia fractures. From the results obtained, it was found that geometry of the epiphysis affects the area applied on the tibia. The distal part of the whole tibia has less surface area in the comparison with the extension where the compressive forces was applied on them. In addition, the surface area of proximal and distal part of the shaft tibia in comparison with the other two models. Besides, The whole bone model has the most voxel numbers. Third, larger the surface area and higher the number of voxels a model contains, the more to distribute, hence reducing the overall stress on the bone. The three models of the tibia were generated by software based on the CTs. The key parameters of the F model including boundary conditions, mechanical properties of the materials, and the geometry of parameters make an important contribution to the accuracy and reliability of the analysis. In addition, the fracture risk of each daily activities was also investigated based on maximum bone missile stress generated. The higher the maximum bone missile stress, the lower the value of fracture risk. The easier the standing is patients, which will not occur at the tibia. However, the tibia high risk of fracture upon the jumping activity. Although yielding the similar results, the bone missile stress and fracture risk models were slightly different. Were affected by the geometry of the third model and also the surface area of the applied compressive force. That's all for my presentations today. Thank you very much.